Yeah, so I'd like to thank all the organizers, Shamik and Arnab and Saurabh for inviting me to this, to give a presentation here. And, it's been a really very interesting meeting and I've learned a lot. I just should apologize that I haven't, been able to participate in breakout rooms or in the Slack and so on. But that's just because it's end of term time here and we are like, it's awful amount of work just now with exams, corrections, projects, seminars, etc. But I'll be very happy if, of course, anyone interested gets in touch now. Really. Okay, so I've kept it a bit light here, and maybe it's stuff many of you already know, but I just thought it's good to be clear. So I'll kind of begin at the beginning and talk a little bit about current fluctuations, finite and short time, and some of our work on this in non-equilibrium systems. Okay, so non-equilibriums imply currents in phase space, and that we know. And I had this picture that I often show from this experiment, which is really nice, of this chlamydomonas, which is just a few micrometers. It's a little algae, just a few micrometers. And what they look at is that they film it like every few milliseconds. They look at the flagella that are sort of fluctuating. And then by sort of looking at the sort of in the phase space of shapes, so they break it up into sort of the three bending modes of a flexible rod. And in this phase space of shapes, they are able to see this nicely circulating current here. And so that's, so that implies broken detail balance and of course, entropy production, as we all know. And entropy production, is also can be viewed as a current. So it's a sort of generalized current. So, and these are all things we've heard in many of the talks, in many of the previous talks. So this current that they've plotted here is a sort of average sort of circulating current. But of course, the currents, you can have also, are fluctuating quantities. So actually, I should also say that, in the previous talk, in Edgar Roldan's talk, he also mentioned, these articles, which I knew about before, of course, also, but, it just reminded me of those that were actually from very much longer back than this, that also sort of considered this case of broken detail balances, P. Martin, PNAS from 2001. Okay, so so suppose I want to talk about, not just means, but also variances and so on. So then, I can very, very simply sort of do it like this, that, okay, I have a system, a bit simpler than our little chlamydomonas, but maybe it has only 3 states. It can take A, C, B, and then I get a time trajectory. So an experimentalist gives me this time trajectory. And I kind of know, okay, that it's described by a master equation. Fine, then I, so let it reach steady state. So for a large part of this talk is going to be steady state properties unless otherwise mentioned. So I let it reach steady state. So imagine now that it has reached steady state. And then, if I want the current in any one link BC, then I just keep track of every forward hop minus every backward hop, divided by the amount of time I've measured this in. That gives me some kind of an estimate of the average. And this estimate of the average would exactly be the theoretical value, but of course that's for large times. But so if I plot this thing, of course, it's not just, I can see that there are also fluctuations. If I plot, say, this link, the current over the, any of these links, A, B, AC, or BC, so you can see that, okay, you can fit a sort of line, so there's a linear slope to it, but it's also fluctuating. And these are the variances that we talk about. And of course, one could also talk of higher moments and so on. Okay, so just to mention, this entropy production was also a current, I said. And so a procedure here would be that, okay, multiply this by some quantity dBc. If this dBc happens to be exactly this, then, and I sum over all links, then I get exactly our entropy production current. Remember, this is a time extensive quantity. So the average is, what we call, so we will refer to the sigma quite often. That's a rate. And the average is just something that is extensive in time. Okay, so again, things that we've heard. Now, if I was to use this procedure to get the entropy production, it would be quite difficult unless I had an enormous amount of data, because I would need to know all the sort of states, I would need to know all the transitions between these states and so on. Okay, but we'll see there are other ways to do it. Okay, so there's one thing that I thought I would just clarify, is that sometimes people get a bit confused. I'm talking of steady states, and then you could say, why is there a time dependence? Okay, the mean, of course, was something that depends on how long a data trajectory I have. But the variance, of course, also depends on time. Just because I can think of it like this: I have this large t trajectory. I chop it up into little bits of tau, and then the variance depends on how long these tau bits are, basically. Okay, so the mean actually doesn't depend, but the variance will. So that's where the time dependence, which is interesting, comes in. And we'll talk of short time or large time, and also when time is neither short nor long, of the variance. Okay, so if you want to get, so if we are going to start becoming quantitative, then we need to talk of models, and we've seen all these different models in all the talks previously. The little ABC model was maybe this sort of given by a master equation. More often in the work we did, we use these overdamped Langevin equations. There are, of course, also underdamped Langevin equations, but I won't talk about those. And in the class of these overdamped Langevin equations, I just have a little cartoon of a bunch of these models we looked at. So these are very simple models on the scale of things, on the scale of models. And so there is this, all of them with, if you have A as sort of linear forces, so colloidal particles in harmonic traps, where these harmonic traps can be, so there's this breathing parabola. You can actually change, sort of breathe in and breathe out the sort of trap parameter K, or sliding, or this model, which I think was first introduced by Sanjeev and Arnab. And then, we'll also refer to this Brownian gyrator. So it's, a two-dimensional model of a colloidal particle in a trap, where you can actually impose different temperatures along the different axes. It's variously known as a bead spring model. And in fact, you can even, so all these things you can realize in the lab, and you can even realize them as these circuits. So there are several of these experiments, and I haven't given any references to these models. Several people have looked at them, of course. Okay, so what do we know about current fluctuations? I said, okay, so let's just think of the mean, rather the variance. So what are things that constrain the variance? Well, of course, we have our fluctuation theorem, but the fluctuation theorem is constraining, it doesn't give you any, sort of quantitative prediction for what a variance should be. It constrains your probability distribution of your total entropy production, but it doesn't tell you, of course, what it should be. But one thing that does do that is, one thing that does constrain the variance is this TUR, this thermodynamic uncertainty relation, which was introduced in 2015 by Andre Barato and Udo Seifert. And what they said then was that, okay, so, at long times, we can sort of argue that this variance is also extensive in time. It goes linearly as t. The mean also goes linearly as t. So now if I actually just have this ratio, variance of this quantity by this, so this is a time-intensive variable, and I multiply it by sigma, which is also time-intensive because it's a rate of entropy production, then all this stuff on the left-hand side is greater than or equal to 2. And this was very generally true, not just for our underdamped Langevin equation, also for master equations. But perhaps not for, not just for overdamped Langevin equations, also for master equations, but not perhaps for underdamped, as Seifert mentioned. Okay, so very soon after that, actually in 2017, a sort of finite time version of this was also shown, first numerically, then theoretically. And that was that, okay, don't, so I remember a finite time was when you chop up your long trajectories into bits of, sort of windows of tau. And there they show that actually it's not just this quantity greater than 2, but it's also this if you just consider the time extensive currents. So all of this here. So we can. So initially the sort of interest here was, oh well, so dissipation, namely sigma, is bounding what your currents can do, bounding the variance of your currents. So that is an interesting aspect. But very soon, it was also, it was it was realized that actually you can maybe infer sigma this way in some easier way than doing it the brute force way that we talked about a bit earlier. So you can actually infer sigma by looking at this quantity. Okay, so this was just everything taken over to the other side, leaving sigma here. And then what this quantity would do is for any of these, any generalized current, this J, script J, you would actually get a bound for your entropy production, so a lower bound for your entropy production. So there was a lot of interest in the TR from that point of view. So what this is, so just to be, yes, so maybe just to mention one more thing is that this, as I said, the entropy production, the total entropy production is also a special kind of current. If you just put that in here, this TUR then predicts sort of a bound on this Fano factor of the total entropy production. And just to give you an idea, if my if my probability distribution of my entropy production was, say, Poisson, then that would be 1 variance upon the mean. If it's a Gaussian, then actually it would be actually equal to 2. So the equality is obeyed when if the probability distribution of the entropy production, total entropy production, was a Gaussian. And the equality being obeyed here also means that then if I actually got the right current in there, it would actually give me not just a bound for this entropy production rate, but the actual one. So of course, then you could ask, when is it a Gaussian? And it has been shown that it's a Gaussian in the equilibrium limit when my entropy production rate is very small, so in a linear response regime. But what we showed was also that it's also in a small time limit. Okay, so I will get to that right away, I guess. And then in that small time limit, I can be arbitrarily far from equilibrium. Okay, so let's get back to our little picture here. And then I have our time series again. I chop it up into this bits of tau, sort of streaks of tau. Okay, so I have mentioned here, also related to roll-down stock earlier this morning, that if I don't observe any currents, of course, I have no hope of getting using this procedure. So this is only if I'm able to observe some currents in the data. Okay, so I may not observe currents for various reasons, like there is some stalling force condition, or maybe I'm not able to observe all the the full phase space. Maybe I'm only able to observe some part of it where there's hardly any current that I can see, etc. So this, of course, only works if I'm able to observe any currents. Okay, so I reach steady state, then I calculate the average and variance over these segments. Then I calculate the sigma L, okay, which for example, could have been the quantity we saw in the earlier slide. And then I can vary this weight function. Remember, this generalized currents I could get by taking our bare current and multiplying it by a weight function. So I could vary the weight function, try to get the maximum sigma L as best estimate. And then my entropy production is guaranteed to be sort of the max. Yes. And our result, what we showed was that actually, if you didn't take, so large segment lengths, rather just chop it up into really small segment lengths, then you just get better and better bounds for your sigma. And in the limit of, this dt going to 0, you actually get the exact value of sigma for underdamped Landau equation. So this procedure doesn't work for, you don't exactly get sigma for jump processes. So overdamped Landau equation. So this was, this was thermodynamic inference of sigma. This is not to say, of course, as I said, that this is the only way to do thermodynamic inference. We've heard about a lot of different ways to infer sigma from data, including weighting time distributions or first passage properties, etc. Also, of course, just looking at the forward upon reverse trajectory probabilities of trajectories, etc. Okay, so as I said, for overtime Langevin systems, this is the quantity that I should be trying to maximize. For discrete state space systems, so there was this work which showed that actually you could, instead of taking this, you could actually maximize this instead, and that works for discrete state space systems. However, this might not be such an easy quantity because remember it's e to the minus j, etc. Okay, so.
Supriya, hello.
Yes, sir.
Actually, I was just wondering, what is this tau going to zero limit? Does it imply that it's a continuous observation?
Yeah, so, okay, so that's a good question, and there's a lot one can say about that. So it's just at the smallest time scale that you can get in your data, basically. So remember, of course, experiments are given to you on some sampling rate. So just for a procedure, just for a sort of to give you a working procedure, you could say, okay, just take the smallest, calculate the variances over the smallest time scale that you got from your experimentalist. Okay, so we'll get a bit more quantitative a bit later.
Okay, so that means our recorded data becomes bigger if we take smaller tau.
Yeah, so you can of course average more. That's true. For a given length of trajectory, you can average more. So that's another advantage.
Okay.
That's certainly true. Yes. Okay, so. Yes, so for this Brownian gyrator, which I referred to, we had this, we looked at the sigma L, so it's an overdamped Langevin system, so I can consider this quantity for different J, okay? So that is all these different kinds of currents. And the best one actually, if you, and this is the tau, this segment over which I chop up my data, and the best one gives you the exact entropy production rate, which in this model, we can actually analytically get everything, and that's 2 here. You see that at very large times, if I chop up my large trajectory into large segments, I get a bound, no doubt about that, but it's actually quite far below the actual entropy. So this dashed blue line is, you can think of it for every tau, this dashed blue line is the bound I get from the best current. Okay. So we looked at a bit, some experiments, which we so far simpler than any of the experiments we've heard about on biological systems, etc. But this was just a colloidal particle in a trap, where the trap is shaken as an Ornstein-Uhlenbeck process. Again, it's something that we can analytically get, and we compared, so the inference that we can do with TUR with the inference, so these two, so forget about these spaces business, but these two are the inference we can do with TUR. And then the SFI is another method, stochastic force inference is another method. We just compared with that. In every case, we get data sort of similar to what this other method gives, and it sort of lies in this window, which we estimated was where it should lie. Okay, so that's one thing. Since then, I think Shrikant has also done other work with Bidisha Sinha's group at IISER Calcutta with looking at, and that's not where I'm not involved in that one, but it's really nice work where they've looked at active fluctuations in active cell membranes, and use this procedure to somehow differentiate the active cell membranes versus their ATP depleted versions. So far we've talked of steady states, but actually, it doesn't matter, because if I'm doing this t going to zero limit, it's the sort of instantaneous value. So I can actually estimate entropy or entropy production rate even for time varying systems. And so this was some work we did with Shun, who was at that time Takahiro's PhD student, and since then he's finished his PhD. So this paper has Shun and Takahiro and Shrikant, of course. Okay, so basically this was just to say that we can also estimate time independent, but that would require a fair amount of data. So in the sense that, and there are other schemes also proposed for time dependent systems. This would require that I have a lot of data, because what I need is actually that at a given instant of time, then I need an ensemble of values. So then I would need a lot of different trajectories. At a given instant of time, I freeze it, and then I take that ensemble of values to get my mean and variance. Okay, so you could say, why does it hold? And the reason is actually at very short times, the fluctuations are Gaussian. And it's sort of like the close to equilibrium regime, where it's known that the fluctuations are Gaussian. But actually, sigma can be arbitrarily large. So you see, it's a rather simple idea, maybe even trivial, sort of when you look back on it, in the sense that this thing can be small, either because sigma is small or because delta t is small. So it's as simple as that. Okay, so so the mean, of course, was something that was changing, increasing in time. The variance is something that's also linear in time. So actually, it's linear in time. We saw in the short time limit. It's linear in time in the large time limit. Okay, so what can we say about intermediate times? Okay, so for that, of course, one has to do a little bit more work. Maybe I should keep track of my time, because with the full screen, yes. So I have some time. I might actually be even done before, but okay. So if we want to get so the full time dependence of, say, so some moment of delta S total, then we have to do a bit more work. And so basically how we looked at it was that we calculated these generating functions. So if we are interested in the speed, the probability distribution of the total entropy production for arbitrary times, then either we try to get it some way, or we try to calculate the generating function from which we can get all the moments. I just wanted to mention that there is this other approach too, in this paper by Simone Pigoletti, which is from PRL 2017, where they derive sort of a Langevin equation for this random variable delta S total. And if in principle you could solve that Langevin equation, you can get all the moments. There's only one subtlety in that Langevin equation, that it's rate of change of this with respect to a time which is some sort of scaled time. It's not actual time, rather it's a scaled time. And to understand exactly how that time is scaled may or may not be possible in several models, but it's an alternate approach to calculating generating functions. Okay, so an interesting result for this generating function, this quantity actually, was that it's bounded at any time, short time, long time, middle time, whatever, by this quantity here. Okay, so it's a sort of parabolic bound on this generating function, and this was shown first numerically in this paper, and then also analytically in this paper. So that's a bound at any time. You can, of course, get a bit more sort of accurate at large times and do with large deviation theory. And so there are many approaches. One that we heard in Professor Kate's talk just before in the morning, but in the context of these kind of models here, this was a paper by Anirban Kundu, Sanjeev Savapandit, and Abhishek Dar, where for a class of models are able to derive this kind of asymptotic form at large times. What we could do actually for this class of models, so what is this class of models? Overdamped Langevin systems. We looked at harmonic potentials and diffusion, which didn't depend on space or time, so simple diffusion. But given that it can be actually arbitrarily dimension, it can have actually arbitrary or large dimension. So it can be a couple sort of generalized Ornstein-Uhlenbeck processes. For those systems, we can actually get this for any time, or even more complicated quantities like this. So this quantity, for example, has if all this lambda q, lambda w, and lambda s were all lambda, then I would just have this back again. But you could also keep them separate to just bring them down, or sort of different combinations of them or different moments, etc. So we can actually get this. So how do we get this? I just had a few technical details here. So we want this generating function of this current And then we can write this in this form, in this with this Onsager-Markov action, which again we've seen in some previous talks. There are also some boundary conditions that come up here. So now what we need to do is we consider the eigenvalue problem of this operator. So remember that operator that there's O, that fancy O, is some matrix. So let's say for our Brownian gyrator, it's some 2x2 matrix where we have actually, yeah, since we have x and x dot is actually a 4x4 matrix. Okay, and then we want to solve it for getting the sort of all the eigenvalues and the eigenfunctions. Okay, so if we can do that, then we know that, okay, in some sense we could, and if we can get rid of these boundary conditions by imposing these sort of these rules here, then we know that, okay, so in some sense this is a Gaussian integral, even though it's a sort of functional determinant. So I somehow have to calculate this functional determinant. We know that at least if it was a finite sort of regular matrix, it would be in terms of the sort of determinant of the matrix. Okay, so but for a functional determinant, that's somewhat harder, but actually it was done by other people. So this is a technique that we used actually, and I'll give you the references in the next slide. So we want to get this determinants, this ratio of the two determinants. Okay, and what was shown in earlier work is that this ratio of these two determinants is actually equal to the sort of ratio of these two analytic functions, which have poles at all the places where this at exactly the place at the eigenvalues of this operator. Okay, so it's a function of the eigenvalues and has poles exactly at the eigenvalues of this operator. If I could construct such a function, then one can show, and this was done in earlier work, that this is the case. And okay, then the question is, okay, how do you construct such a function? And there the boundary conditions play a role there. Okay, so these are some of the references actually, and the work I'm referring to, we actually learned about this in this work of Nicholson and Engel. But that was based on earlier work by Engel in 2009, and he based it on earlier work by Klaus Kirsten in these other earlier papers. Really very, very well written and nice papers. So all the work we did actually, or Shrikant did in his PhD, was based on this. And we are actually thinking a little bit about, so we have these techniques. I mean, one new thing that we did was actually that Engel and Nicholson, as well as Engel, didn't, use this method in the context of generating functions. So what we realized is that we can actually use it in the context of evaluating generating functions. And so now we are also interested in thinking a little bit about how this method, for example, compares with other methods which exist, which I might have actually written here. Yes, in fact. So for example, there is a, so in Professor Park, a group, Professor Park's group in Korea, also they have looked at this Brownian gyrator, and they have some, expressions for these generating functions as a function of time. But it's a slightly different method. So we were interested actually, so there's this whole slew of methods available. So we were interested in a bit comparing, and so that's something that we are thinking of doing with Shrikant and Deepak and Ralph. But as I said, this is a method that's been around. Okay, so what can you get with that? Well, so you can actually, get explicit expressions. You can get the generating function. You can, of course, get the moments. You can get explicit expressions, which sort of look like that. So if you look at this expression, for example, for the variance, you can see, okay, tau going to zero limit, it's going to a constant. Okay, remember, I've sort of divided by tau. So then the variance goes to a constant. At tau going to infinity limit, it goes to another constant. In between, it's doing whatever. So you can actually get the finite, all finite time dependencies for what it's worth. You can also get one other thing, and this might actually be my last slide, actually, yeah. So the other thing that we've done a bit more recently is that we've looked at this skewness, which is a sort of the third centralized moment upon the variance to 3/2. And we see that in at least in these overdamped Langevin systems, even if they are non-linear, so there's some numerical work on that as well, the skewness is sort of non-monotonic, starts off at 0, increases, goes back to 0 again, and it seems to get more and more skewed as we look at systems which have larger and larger entropy production. So this was analytical from our expressions, and this is actually the experiment seed too, because there was a question of, is this time that this becomes non-monotonic so small that you can't see it in experiments, but actually we can. And the skewness has an interesting consequence because so we were that's how we originally thought about it actually, and so we looked at also these quantities T plus and T max, which were introduced in this paper by Barato et al. In this PRL, where they say that at large times, so if we look at this entropy production, there are large stretches, and we want to understand, say, some behavior of the fluctuations. It could either be sticking close to the average, it's sort of fluctuating around the average, but sticking close to the average all the time, or there could be large stretches which are above and below the average. And so what they said in this PRL is that actually it obeys an Arc-Sine law and at large times. And so there are large stretches above and below average, and you can quantify them by this quantity T plus. So the fraction of times it's lying above the average, for example, or T max, the time to the supremum in a window of time. And if it was actually following the Arc-Sine law, it would exactly be there on the dotted line, or it would be here. But of course, because of these time-dependent, skewness behavior, it actually lies below for a considerable fraction of time before it goes to the 0.5. And yes, so I think with that, I'd like to stop even 4 minutes in advance. Thank you for your attention.
Thank you very much, Supriya. Any questions?
Hi, can I ask one question?
Please do.
Hi, Supriya, this is Vijay. Hi. So one question I have, is it very obvious the skewness is always positive in this problem?
Yeah, so I think you can show that it's not just the skewness. I think you can show that all moments, all cumulants are actually positive.
Okay, this is very specific to this particular setup, right?
Do you mean that the skewness is positive? No, I think it's not particular to this setup. I think it's almost some kind of consequence of the fluctuation theorem, I think. So I have to think a bit more carefully about that, but I think you can show that all cumulants are positive.
I see. Okay, great. Thank you.
You're welcome.
Further questions?
Supriya, it's Arnab here.
Yeah, hi.
Yeah. So somewhere you mentioned about Brownian gyrator or something. Maybe is it? So I missed that point actually. So
yeah, so it was just one of these many models we looked at. So it's a 2D. I have a picture here. It's a sort of colloidal particle in a 2D trap, harmonic trap. And the sort of the axes of the trap are slightly tilted with respect to the temperature axis. But you can keep the system out of equilibrium. Alternatively, you can think of it also as this bead spring model. So here are these two. I don't know. Can you see my? I hope you've been able to see my.
Yes. I'm able to see. Yeah.
Yeah. So you can keep these two beads and you can keep them out of equilibrium by kind of keeping them at different temperatures. And of course, you can have as many beads as you want. But if you have two of them, that's typically called the Brownian gyrator.
So here in this case, in Brownian gyrators or in this bead spring thing, that you also measure currents and bounds to these currents, right? Because they are
Indeed.
out of equilibrium system.
Yes.
But there is no explicit time-dependent drive to these systems, right? Because you have this
very correct. You don't. So you see in these very correct. So you don't. But you don't need. So take a look at this overdamped Langevin equation. Okay, so B is a diagonal matrix, whatever dimension, so we don't have to worry about it. Take a look at this A. I can have non-equilibrium behavior without time dependence if I have forces which are non-conservative. So that translates to this A not being a symmetric matrix.
Yes. Yes. Okay. Okay then. Thanks.
Yeah. I should say that generating function thing works actually for some time dependencies, some kind of time dependencies, such as, for example, this breathing parabola case where I have the trap stiffness as a function of time.
Yes, but it is not necessary to have the out of equilibrium situations, the time dependent protocol or something. You can have some different, the temperature gradient or some kind of external gradient to drive the system
Right.
far from equilibrium.
Right.
Thanks. Yeah.
Further questions? We still have several minutes before the next talk is due, so don't be shy. I do have one question, Supriya. You talked about overdamped Langevin, you talked about some discrete Markov processes. Have you thought at all about inertia? Because there's this strange result that Patrick Zonka
Indeed.
came up with recently.
Yeah, that's right. So that's not a result I've understood, even though I've had the chance to hear Patrick a couple of times by now. I actually haven't understood it. So basically for the others, and I think Udo Seifert mentioned this in his.
He did mention it. The thing is that it seems to me that
if you have this, then TUR can be violated. So
yes, but
I believe, however, that there are other bounds that exist for this, for underdamped Langevin equations. Okay, so there are two qualifications. If it's a one-dimensional one, I think the TUR still holds, but we haven't looked at it. That's what Patrick mentioned. It's only if it's two-dimensional that, in some cases he finds this TUR violation. But we haven't actually thought about it.
But there's no, in your discrete time processes or the jump process you also mentioned,
yeah,
there's no restriction there as far as you know on the classes of dynamics for which the results you described today.
As long as they are Markovian, sort of.
Yeah.
Yeah. There's no restriction as far as I know.
Okay.
As long as they're Markovian. Right.
Okay. Well, so if there are no further questions, last chance. If not, let's thank Supriya again. Thank you.
Now I'll stop sharing.